Okay, so we're going to look at inverse functions. They're derivatives. There is a shortcut to do it rather than going the long way of finding the inverse function. But I wanted to review just a little bit about inverses so that you understand what it is that we are actually doing. So you know f of x is the original function, and its inverse is written as the inverse of f of x. Okay? And they're interchangeable simply by what we learned back in Algebra 2, where you're just essentially flipping the x and the y. What becomes a little bit difficult to understand is how we're going to use it with calculus, to where, let's say we have f of x, which gives us a output y value. Okay, so f of x is equal to y, we could say. And then we have the inverse of f of x is equal to another y value. Let's analyze what this means. This input in the original position function will yield a y value that again is on the graph, if you will. And something that we're going to see of how it relates to the inverse function is that, this is very important what I'm about to say, the input of the original is actually equal to the output of the inverse function. So whenever I have a graph that looks like this, okay, and I'm looking at it as far as this xy is a point on the original, original f of x, and this xy is on the inverse function, and you're going to have an x and a y here. Notice how I'm highlighting. The input of the original is equal to the output of the inverse. Vice versa. The output of the original is equal to the input of the inverse. Okay? So one function's input is the other one's output, vice versa. Okay? All right. And what we're looking at are these properties that g is the inverse of f and f is the inverse of g. So the domain, otherwise x values, is equal to the y values of the original. Okay? So this is saying the input of the inverse is equivalent to the output of the original. Okay? And vice versa. Not every function has an inverse, but if a function does have an inverse, the inverse is unique. Alright? Let's look at the following example. It says, given f of x is equal to x cubed, and the inverse function is the cube root of x. Okay? And if I were to evaluate f of 2, I'm just going to plug in 2 into the f of x function, which would give me 2 cubed, which is 8. Okay? Now, if I looked at this and I evaluated the inverse of f of x evaluated at 8, I'm simply going to grab this 8 and plug it in to my inverse function. I would get the cube root of 8 is 2. Notice the relationship here. I have the input of the original is 2 is equal to the output of the inverse. And I have the input of the inverse is equal to the output of the original. That's huge of how we're going to use this shortcut here in just a bit. Okay, so f prime of x is equal to 3x squared. Therefore, when I plug in the 2 into this derivative, I'm going to get 12. Okay? It says, what is the derivative of the inverse? And it is called the derivative, so the derivative of inverse of f of x. Okay? So, the long way is we would find the inverse function, which in this case was the cube root of x. And then we would take its derivative. Okay? So imagine that we rewrote it as the inverse function is the cube root of x. And when I take the derivative, I'm just going to use the power rule. 1/3 x to the minus 1, which in this case would be a negative 2/3. And then if I rewrote this so that it wasn't with negative powers, it'd be 1 over, 3x to the 2/3. Otherwise, the cube root of x squared with the 3 multiplied in the denominator, and I get this function here. Okay, that's my derivative of the inverse, which is the derivative inverse of f of x. Now, if I plug in this 8, the input of the inverse function, and this is the derivative, I'm essentially going to plug it in over here where I see my input value of x waiting for me to plug it in. So I get 8 squared is 64, the cube root is 4, so I would get 1 over 12. Okay, so 1/12 would be, if I asked you, find the derivative of the inverse function evaluated at 8. And look what we notice. Notice that in our answers, C and F, that all they are reciprocals of one another. Okay? So there is a relationship that lends us to this shortcut that we can use when taking the derivative of an inverse of f of x. Okay? And it's right here. So first of all, we have our equation right here. Okay? And it's on the left side saying the derivative of the inverse of f of x evaluated at a certain constant. Okay, so it's not just saying here's the inverse of f of x. It's not just saying take the derivative. Okay, it's saying take the derivative and at a certain a value, at a constant. Remember, a through e are all constants. Okay, and that's just a good way to remember is e is 2.718 as far as the constant is concerned for natural rate of growth. And this equation is going to use a certain input that we're going to find as far as that we're going to be given as far as what is our a constant input. Let's go ahead and get to the example. It says sometimes we are given all of the pieces we need and then we just need to put them together to get the answer. For instance, we are looking to find the derivative, so the derivative of the inverse of x function, but specifically evaluated at 5. Okay? So again, yes, you could establish what is f of x. Then you could find its inverse. Then you could take that inverse's derivative. And then last but not least, step 4, you could plug in 5 into that derivative of the inverse function and then get your answer. That's a lot of steps where we could simply see the pieces that we've been given and actually use this equation, shortcut if you will, to find what that derivative would be as far as what's the answer of this right here. So let's go ahead and get started. The inverse of f of x, the derivative of it, evaluated specifically at 5, we're just going to copy over the equation, which is 1 over f prime, and it's the inverse of f evaluated at 5. Now, notice, this right here is key to using the shortcut. I'm going to plug in 5 into this inverse function of f. Okay? So the way I want you to read this is 5 is the input of this inverse. Okay? And 5 being the input or x value of the inverse is going to be the same, so it's equivalent to the output y value of the original f of x. Okay? So this input of 5 that I see on the inverse, I can actually look at it also as the output here of the original f of x. Okay? Now, what this in red is going to find, it's going to yield an output value on the inverse function. Okay? And an output value on the inverse function is the same as the input value for the f of x, for the original function. So all of this in red right here is basically the same as saying the output of the inverse. Now, what is that the same? That is the same as the input of the original. I'll say it again. The output of inverse will be the same as the input of the original. So essentially, when I see this 5, I'm going to put it as my answer y value in the original f of x, and then solve backwards for my x value, which means all of this will become 3, which is 1 over f prime of 3. Again, what did all this in red say that we were looking for? It was going to yield the output of the inverse, which is the same as the input of the original. Okay, so now from here it's easy, because all I have to do is take the derivative of f of x, okay? Take the derivative, plug 3 in it, and then take the reciprocal, okay? So let's see what we have, what pieces we were given. So f prime at 3, okay? F prime at 3 has been given to us as 7/2. So all of this denominator is 7/2. And all it is at the last step is just the reciprocal of that, and that is the derivative of the inverse function evaluated at 5 would be 1 divided by 7/2, which if you wanted to do it by hand, keep, change, flip, is the same as the reciprocal of 2/7. So 2/7 would be the answer here. Okay, so that's how you use the shortcut. Let's do some more practice. Okay, we are looking for the inverse function evaluated at 2. So I'm going to start off by saying, here's my shortcut, which is 1 over f prime of the inverse at 2. Okay, so let's look at what we just wrote in red. Okay, so 2 is the input right here of the inverse function. So where am I going to put this to? I'm going to put it as the output of the original. So the output is 2 is equal to my original function of the following. Now, when I solve for x, here, it's the same as what all this in red is representing. The input of the original function is the same as the output, which is all of this y value answer of the inverse. So the input of the original is the same as the output of the inverse. So let's solve backwards and solve for x. Okay? Because once we solve for x, we'll say 1 over f prime of whatever that is. So when we solve backwards, whatever we get over here for x, that's what we're going to put right here for our input. Okay? So we'll have, let's see. I have a cubic function. I'm going to go ahead and set it equal to 0. So it's going to be minus 3. And you could test point some things right now as far as test out some integers like 0, 1, 2, 3. Just plug and chug. And we see that x is equal to 1 does work. Now if you didn't want to do that, you'd have to do rational root theorem, which is your leading coefficient, all the factors of it, which is just 1 and 1 in this case, and then your last term, all the factors of it, 1 and 3. And then you have plus or minus combinations. That means you could have 1 over 1 or 1 over 3. Okay? So plus and minus 1 over 1, plus or minus 1 over 3. So essentially you have 4 numbers that you could test to see synthetic division wise, 1, 2, negative 3, which one of these 4 would work. So we see that 1 could possibly work, and synthetic division will say that my remainder is in fact 0. So this was a 0 of this function, which means it was a solution, and now I can put 1 right here. So now from here, all I have to do is just take the derivative of my original f. So this is f prime of x. So I just have to take the derivative of this, which means f prime would equal 3x squared plus 2. And this one answer that I got way over here, that I put here as my input value, I'm going to put it right here for x. Okay? So let's go ahead and put that right here. So it would be 3 plus, or 1 squared is 1 times 3 is 3 plus 2 is 5. But again, it's the reciprocal, so the answer is 1 over 5. Let's do another example. Okay, so the inverse, the derivative of the inverse evaluated at 2, okay, let me put this, this is going to be 1 over f, or in this case, g prime. So g prime at the inverse of g at 2. Okay, so here we go. This inverse, this input on the inverse of g is the same as the output on the original g of x. So I will put 2 is equal to, let me make some room over here, is equal to the square root of x plus 1. Now all I have to do is solve for x. Okay, so I'm going to square both sides. I get 4 is equal to x plus 1. Then subtract and I get 3 is equal to x. Okay, that means I'm going to now rewrite this as, here we go, 1 over g prime of this set value of 3 that I found. Okay, so now let's derive the original. Okay, let me make some room right here, so that we get g prime of x is 1/2 of the stuff to the negative 1/2 times the derivative of the inside, which is just 1. So that's 1 over 2 square roots of x plus 1 without any negative powers. This is g prime of x. We are going to plug in this 3 value that we solved for over here, right here for x. And we get 3 plus 1 is 4, the square root is 2, so this is 1/4. So it's 1 over this 1/4, because again that last step is the reciprocal, so that the answer would be 4. Alright, let's do one more example. This is what I'm looking for. I notice it's the derivative of the inverse. So by memorization, I go to the derivative of the inverse of f of x, evaluated specifically at root 3 over 2, is the same as 1 over f prime of the inverse of f at root 3 over 2. Here we go. This input of the inverse is going to be the same as the output of the original. So I will put root 3 over 2 is equal to my original function of cosine of x. Now notice my restriction. I'm talking about in the first and second quadrant, which is from 0 to pi. I'm going to see when is the cosine of an angle equal to a positive root 3 over 2. So positive, it has to be over here, because this is negative, positive. And again, cosine is looking for x values. So we're going to look right here in quadrant 1. So we have 3, 2, 1. And here's my x value of root 3 over 2. And sure enough, it came from x is equal to pi over 6. Remember, we are always in radians in calculus. Okay? So pi over 6 was the input that this came from. Okay, remember that means that that is the answer that is here, solving backwards per se. So we have 1 over f prime of this pi over 6 that we found. Now we just have to obtain f prime by deriving the original. So let's obtain that by taking the derivative of that. And we have f prime is equal to a negative sine of x. Okay, so now we're going to plug in our new found value of this pi over 6 into right here our derivative function. So let's plug in pi over 6 and we get f prime of pi over 6. When I plug it in here, it means the sine at pi over 6 is 1/2. And it has a negative in front, so it's a negative 1/2. So all of this denominator just became that negative 1/2. So if I take the reciprocal, yes, my answer becomes negative 2. Okay. Let's review some stuff from before. Let's talk about now derivatives of exponential functions. Okay? The derivative in respect to x of e to the x is itself, in fact. But this u is saying, what if it wasn't just x? Okay, so this u right here is symbolizing that it could be like e to the 2x or e to the x squared. This u is against anything that is not just the letter x. It's a composite function. It's a composition of other things where it does not have a coefficient of positive 1, nor a positive and or a power of positive 1. Okay? And the rule of this is it's a little bit chain rule. It is the carbon copy, and you can say it if you want, times the natural log of the base, but you don't need it because it's just going to become 1, times the derivative of this guy. So du dx, because it's in respect to x. Okay? Now again, this isn't required if and only if my base is e, because it will cancel to 1. But it is required if my base was like 2 or 5 or 8. Okay? All right, so let us go ahead and start using the derivative. And I know we've done this, but we're reviewing to prepare for integrals of these bases here in just a bit with u substitution. Okay, so y prime is equal to the carbon copy times, again, you can write the natural log of the base, but you don't need it because the base is e, times the derivative of the cream. So we want to find what is the derivative of that power, and we're going to chain rule multiply it. So it becomes 6x times 6x. And yes, you could write it if you want like 6x times e to the 3x squared, and that would be your answer. We got a little product rule going on right here. So it is, the derivative is the first times the derivative of the second, which my rule is carbon copy, times the natural log of the base, times the derivative of the power. Notice my use of parentheses so you don't think that I'm subtracting 2. So, first times the derivative of the second plus the second times the derivative of the first, which is just going to be 3x squared. Okay? And this is the answer, but again, we need to get comfortable with changing negative powers to positive, because that's most likely the simplified form that you're going to see on multiple choice parts of the AP exam. So I know that this piece is going to be in the denominator, and the other pieces would be in the numerator, to where it could look like the following. Okay, so I've moved this negative 2x to the bottom, making it positive, and I'm going to add the 3x squared, and again moving the other one to the bottom, making it positive. So this is an equivalent form of the derivative. And yes, if you'd like to combine those two together to something that looked like this, most likely that would be your simplified form. Let's look at part C. Part C is the derivative of a natural log. It's been a little bit, but we've done this before. It is 1 over the stuff times the derivative of the stuff. Let me make some room. So now that I'm going to take the derivative of the stuff, the derivative of 5 is 0, and the other part is the carbon copy times the natural log of the base times the derivative of the power. So all of this could simplify to 4e to the 4x all over 5 plus e to the 4x. This would be the derivative. Now, just a little bit reminder, please do not cancel those, because you can only cancel like that if there are between pieces of multiplication, which in this case, it's not that case because I have an addition on the bottom. So what you see right here, it would be an acceptable full answer. Okay, so let's get just a little bit more practice with this before we start doing the integrals here later with exponential functions. All right, so we're going to pick up the pace just a little so that you can see the steps and processes. Find the derivative. Okay, we have another product rule. The first times the derivative of the second plus the second times the derivative of the first. And this is an acceptable answer. There are no negative powers, that's good enough. Over here, I do not split this up into two different, this is a common mistake people make. You don't split it up into two like this. You only do that when the bottom denominator has one term, which is not the case here. So this, in fact, would be, the second question is, would I bring this up with a -1 power, if you will? The answer is no, because the top is not just one term, that is a constant. So yes, this is a low, oops. So it's a low d high, which is carbon copy times the natural log of the base, times the derivative of the power, minus high d low, which again is carbon copy times the natural log of the base, times the derivative of the power. All over low squared. E to the 3x plus 4. This is that low piece. I have no negative derivatives or powers whatsoever. This could be a final answer, acceptable answer. Okay? Now, let us look at this example. And what we're going to do is, we are going to use recent tools that we've learned by breaking up this trigonometric function of tangent into two fractions, or two pieces, a sine of t over a cosine of t. Okay, notice how we do this. First of all, u is cosine of t, because du is negative sine of t dt. Notice all of this that we just picked up right here in the original. We've done enough u substitution by now to know that the rewrite is going to be this negative, and it will be 1 over u du. We just have to now be careful of making sure we change our bounds, because we're about to transfer over to in terms of u. So let's go ahead and plug in 3 into my u substitution. Okay, so that we would have the cosine of 3. And then we're going to come over here and plug this into our t, so that we have the cosine of e to the 5x. And already you should be looking at this and wondering what's going on here, because you have a lot of natural logs and you have the cosine in e here. You can approach it like this, but this is too much work. Okay, I just wanted to show you a little bit of practice with u substitution, but also show you that there's a much faster way to get the same answer, if you were to finish that out, of simply knowing that we're taking the derivative of an integral. So we're wanting to find the derivative in respect to x from 3 to e to the 5x of our integrand known as tangent of t. And yes, the shortcut is take that integrand, put parentheses where the t goes, that's f of b, minus the same thing. And now we're ready to plug in our top bound of e to the 5x times the derivative of that limit, which is going to be carbon copy times the natural log of the base times the derivative of the power, which is going to be 5. So you could have written that as 5e to the 5x if you wanted to. Okay? So 5e to the 5x. Plugging in the 3 and multiplying by its derivative of 0, you know all that zeroes out. So you don't even need all that. So that the answer for this one, per second fundamental theorem, would simply be that. Alright, write the equation in the tangent line. Okay, so I see tangent line, and I'm thinking my point slope formula. I know that I need a point, which 0 would go here, and 1 will go here. Now I just need to find the derivative, otherwise the slope, of this evaluated at 0. So let's find y prime. It is a carbon copy times the natural log of the base times the derivative of the power. So it's 2e to the 2x. And we're basically going to plug in our 0 into this x value right here. Okay? This is our at value. So 2 to the 0 is 0. So e to the 0 is simply going to simplify to 1. So it's 2 times 1. The slope is 2. So it'll be 2 here for the slope. X minus my x value here from the point, and then y minus the y value from the point. And you can leave it like that, or if you wanted to simplify, you could say 2x plus 1. You don't have to simplify that, but you can if you want. Alright, so now let's do this implicit differentiation over here. It is 3x squared plus, here we go with product rule, we have the first times the derivative of the second. Careful. Carbon copy times the natural log of the base times the derivative of the power. Okay? So that's first times the derivative of the second plus the second times the derivative of the first, which is just 1. And you can write it in, or you can just close up the parentheses. Keep going with the derivative of y to the fifth is 5y to the fourth times, this is implicit, dy dx is equal to 0. Now remember, our goal is to get these dy dx's by themselves. So quickly I want to identify where are all my plus and minus pieces so that I can see what's going to end up GCFing, what needs to distribute, so on and so forth. So, multiplying, there's nothing really here to distribute across these, okay? Just a positive 1. So we have 3x squared plus x e to the y dy dx plus e to the y minus 5y to the fourth dy dx is equal to 0. Now you can see these are going to stay on the left side. Okay, and you can GCF out the dy dx so that you have x e to the y minus 5y to the fourth. And over here on the other side, these are going to be moved over by addition or subtraction. So we have negative e to the y minus 3x squared, and that will be divided by all of this. So it will look something like negative e to the y minus 3x squared all over x e to the y minus 5y to the fourth. And this is your dy dx now all by itself with no negative powers. That looks good enough for me. Alright, that's it.